Next up, we're going to talk about some of the characteristics of species that we see in the oceanic epipelagic, starting with predators. So again, we have this open water, lots of light, right? Because it's clear water, so it's very easy to see through. And it's just open space, right? So there's nowhere to hide either. It's just open water, nowhere to hide, lots of light is like the environment we're talking about here. So this tends to favor predators with strong senses, particularly visual sense. So you have a lot of organisms with large eyes, because yeah, and you can see for a decent distance. So you might as well have these like powerful large eyes so you can see these long distances. Whereas if we're somewhere, like San Francisco Bay, the visibility in San Francisco Bay is often like 10 feet. So you don't need eyes that can see for like, 500 feet. So you're never going to be able to see that far. But here in the open ocean with this crystal clear water, you can see very far. So you have these more powerful eyes. Also, very powerful hearing as well, often seen. And the ability to swim fast. Again, there are no obstacles. So you might as well be able to swim like a race car, just like going as fast as possible. And also endurance as well. Because again, no barriers. So you can just keep swimming and swimming and swimming and swimming. So if you're going to catch, whether you're a prey species or a predator species, it's beneficial to swim fast and to be able to swim far. Because you're not going to be like hiding in a reef. You're not going to have to like maneuver around a bunch of rocks, going in and out of like little rock spaces. There's none of that because it's just open space. So fast and high endurance is the name of the game here. So again, some of the senses we see large, well-developed eyes. Like this is a swordfish right here, and you can see how big this eye is on the swordfish, and it's a fairly well-developed, complex eye as well that we see in swordfish. They also have often a very powerful lateral line. So a lateral line is this line that goes down the body of the fish. Sometimes it's very visible, sometimes it blends in a little more, but pretty much all fish have this. And what this is a bunch of little kind of gel canals with these little sensor cells called hair cells. And what it does is it allows fish to have this sense of water movement around their body. So they can have this very fine sense of how the water moves around their body. This is useful for a few things. First, if something swims by you, you'll like feel it go by, and so you can be like, oh, there was something there. But this is also really helpful for schooling behavior. So those fish that all cluster together, and they also almost seem like they're like sharing a brain, so they'll like move in unison. The way they do that is with these strong lateral lines. They're able to sense the movement of like every single fish around them, so they're able to kind of coordinate and like move almost as like one unit. And again, you also often have very strong hearing or strong smell in the case of like sharks and things like that. You also see in the epipelagic. So fast swimming. Many fish are optimized for speed and endurance rather than maneuvering because there's nothing to maneuver around. There's still like you have to turn and stuff maybe if you're chasing prey, but yeah, you're not maneuvering around kelp or rocky reefs or coral reefs or anything like that. There's wide open space, no obstacles. So often fast and high endurance swimming is what you want to go for. So many of the fish in the oceanic epipelagic have very streamlined bodies, these very like torpedo shaped bodies. We say torpedo shaped, but of course torpedoes are actually shaped like them. They're not shaped like torpedoes. Um, they often have very thin, stiff fins. So if you see things like coral reef fish, they'll often have these kind of more fan-shaped, very like flexible fins where they can kind of swim with their fins, they can maneuver, they can do all this stuff with their fins. Whereas these guys, it's like little airplane wings. They are very stiff, very dense, very thin as well. So you can use them for steering, but they also, many of the fins are able to, when we're talking about like tuna, they can actually slot little grooves in the body. So they're like, chunk, chunk, and they kind of go into these little slots on the side of their body to again make their body like perfectly smooth when the fins are up like this. It's very cool. You'll see if you ever get close enough to a tuna, you can actually see the little grooves where the fins like slot in like landing gear, and they can just like, and they just become these really streamlined little torpedoes. Many of these species also have things like keels and finlets. So finlets are these little triangle-shaped fins along the tail here. And it's not as easy to see, but a keel is this little bit that sticks out on the sides of the tails. These are both used for kind of both reducing drag and keeping the fish straight in the case of the keel. So when they're going really, really fast, they don't accidentally like while they're going super fast. The keel kind of helps keep them upright in the right orientation. Some of them actually have mucus or oil to cover their skin, again, to make them like even more streamlined. Many of them have also lost the scales on like the sides of their bodies, again, to make them even more smooth in texture and go even faster. Most of them, yeah, don't have spines either. Many fish on reefs and things like that will have spines for like protection or for other purposes, and these guys usually don't have spines. So then you get these like fish that are highly adapted for speed and endurance. Things like some tuna species actually migrate across the Pacific Ocean. So they're swimming thousands of miles back and forth, and they can do it pretty fast. You covering them like around 40 miles per day. While also like feeding and stuff like that too. So they're able to do this really high endurance, fast swimming. The fastest fish in the world is also found in this environment. That is the Indo-West Pacific sailfish, which is this guy here. And this fish can go up to 70 miles an hour. So it is a fast swimmer. That is like just mind-boggling to me how fast it is at first swimming speed. So this is kind of just a diagram showing some of the adaptations we see for these like fast endurance swimming. Again, there's these grooves. So like this guy has a dorsal fin, but dorsal fin can also kind of like go down and like slide into a little groove so that it's not sticking up at all. And again, you have a super smooth torpedo body. Grooves for the fins. Again, there's that keel on the side of the tail, the little finlets to reduce drag, swept back points on the tail, very narrow to be highly efficient swimmers. So these very efficient, very fast swimmers. Another thing we see in some of these species is thermoregulation, and this is not something we usually see in fish. So, thermoregulation is kind of not exactly, but kind of the same thing as being like warm-blooded. So you're regulating your body temperature, and we usually think of things like fish as cold-blooded, where whatever the water temperature is, that's what their body temperature is going to be. So their body temperature goes up and down with the water temperature. Whereas us, we do thermal regulation. We're mammals, right? So our body temperature is always the same, regardless of what the outside temperature is. So again, we typically think of fish as cold-blooded, but there are a few, including these guys, that actually can do some thermal regulation. They can make it so their bodies are a little warmer than the water outside. And the way they do this is they have this red muscle on their bodies. And you may have seen this, if you've ever seen like the really nice cuts of tuna that it's like dark, dark red. So this dark red muscle on their bodies, and they're generating heat. Their muscles are generating heat as they're swimming. That's interior to their bodies. And then they have this really cool way their blood vessels are set up so that as blood's flowing towards the surface of their skin, where they're going to lose that heat, they have vessels going opposite directions right next to each other. This is called countercurrent exchange. I'll talk about it more when I talk about also how fish get oxygen out of the water when we talk about fish. But countercurrent exchange, basically the way it works is it allows the maximum amount of heat to get passed to the blood that's going back to the interior of the body. So again, it's conserving heat by constantly passing heat, kind of recycling heat back to the middle of the body. Based on the fish's, again, like the way the vessels are set up in the fish's blood flow. So that allows them to often have their interior bodies be several degrees warmer than the water outside. And that's because muscles can operate a little more efficiently when they're heated up like that. So that's why it's good for them. Many of them, some species also will have these specialized blood vessels around their eyes to also keep their eyes warm, so that their eyes are kind of working again at maximum efficiency as they're hunting. This red muscle is also very good for sustained effort for like endurance. So most animals have like basically dark muscle and light muscle, or red and white muscle. White muscle is good, better for like sprinting, for very fast, short duration movements, whereas red muscle is good for like long duration events. Basically because it has more of what's called myoglobin and can store more oxygen. So again, it can like work for longer. But yeah, and many fish, it's like mostly white muscle, but things like tuna, sharks, sailfish, they'll have a decent amount of red muscle as well. All right. So this was a very cool example of a fish that has is very adapted for like a special kind of very fast movement are flying fish. These are very cool members of the oceanic epipelagic. They're called flying fish because they fly, or rather they glide. they're able to kind of launch themselves out of the water. They have this long lower tail fin that kind of helps to set them up so that they're kind of going in the right way. They're able to kind of steer a little bit as they set themselves up. Then they have these elongated pectoral fins here that look and act like little wings, and that allows them to glide out of the water. Sometimes for very long distances, like hundreds of feet, they're able to glide out of the water. So it's usually much shorter than that. And they use this to escape predators because, if, say, a tuna is chasing them, they can leap out of the water and just glide out of the water. So from the tuna's perspective, it's like they just disappeared because they went out of the water and the tuna's like, oh, they're gone. So very cool adapted fish for the epipelagic. I got to see some of these on some of my research cruises, and it's amazing. They look fake because the boat would be going along, and every now and then a little flying fish would get scared by the boat, so it'd be like it'd like glide off across the water. It almost looks like a little skipping stone going out across the water. Very cool. And yeah, some of them can go very far. So next up, we're going to talk about, camouflage in the epipelagic. Now you might be like thinking, wait, camouflage? There's nothing to camouflage with. It's just water. There's nothing to camouflage. Where are you supposed to camouflage? So there's a few different things that species will do to camouflage in the epipelagic where there's no seaweed, no rocks, nothing to really blend in with except the water itself. And importantly, the light. So many fish in the epipelagic, and also some fish not in the epipelagic, have something called counter shading. Also not just fish. You see this in mammals and in birds as well. So counter shading is where you have a lighter belly area and a very dark top area. The way this works is, say you're like below the shark looking up, this light belly area will blend in with the lighter surface water. So that's kind of blending them in with the lighter surface area. And if you're looking down at this shark, you're going to see this dark top area. And if you're looking down at them, that dark blends in with the dark water below. So it's a form of camouflage that helps them blend in whether you're looking at them from the top or from the bottom. There's also something called counter illumination. This is the same thing, except also with bioluminescence. So this, I believe, is a hatchet fish. It lives in kind of the mid-water, and it is very silvery in color, and it has some counter shading, but it also has counter illumination, where on the bottom of its body has these little things called photophores, which are these little kind of sockets that can light up. And so if you look at the fish from the bottom, this is what it looks like, where it's shape and will be broken up by these little light patches. Also, again, the light coming from the bottom of the fish blends in with the light coming from the surface. So it helps them to blend in when you're looking up at them. So that's counter illumination. So just like counter shading, except also you are producing light. Next question for you guys is, we've been talking about epipelagic fish and other animals. Would you expect animals in the very deep sea to also have counter shading? Why or why not?